So we're going to do a little activity soon that's called the rational tangle dance, which was first introduced by, I don't know if it would have been Conway. John Conway is the mathematician at MIT who sort of developed the theory of tangles in the 60s and 70s, and proved a lot of the foundational results around how tangles work and why they work the way they work. And math educator types have adapted this rational tangle dance as an introduction to how, what are the kinds of questions we can ask about tangles and what's the theory behind it. And so the way it works is as follows, just to introduce to what tangles actually are. So tangles, as we talked a little bit about last time, are kind of a middle ground in between thinking about knots on the whole and just sort of zeroing in on the idea of crossings and really focusing in on crossings and how crossings interact with one another to determine the structure of a knot or a tangle. So today the object of study is tangles, and a tangle describes not a knotted piece of rope, but really sort of two strands of rope. So I've got two ropes in different colors here. And in the rational tangle dance, the dance begins with the two ropes in just a horizontal parallel configuration. So one rope going this way and then another rope going that way that aren't crossed in the beginning. So we call that an empty tangle, and I'll represent that just with this kind of diagram here. And so the idea is that during the rational tangle dance, there are four dancers, the four of you, and you're going to be standing at the four vertices of a square, rectangle, whatever. We'll try and do the best we can with the space that we've got here. And then the dance has two fundamental moves involved in it. We call them the twist and the rotate. The twisting maneuver, we're going to fix an orientation on how we do this. So for a twist, we're going to take the two people that are on this side of the diagram, and they're going to trade places with this person putting their corner of the rope over and the person on there going under. So we'll call that the twist, and we'll denote that with a T. This is what it looks like when you perform a twist on an empty tangle. Obviously, if we have a more complicated tangle sitting over here, then we're still going to have some more complicated stuff, and then we're going to have this little extra twist over on the right-hand side. So in those situations, what we'll usually do is denote the tangle with this sort of block in here. So here's my tangle. I'm going to call it G. And the effect of a twist is, again, it just takes these two people at these sides, and it twists the over and the under, so that what we get afterwards is the same tangle in the middle, G, whatever it is, but then now we've introduced an extra twist over there on the right-hand side. So that's what T does. So rotating, of course, is exactly what it sounds like. It's everybody rotates, and for our purposes, we're going to rotate clockwise, which is going to be around in this way. Clockwise as we're looking down from the ceiling, if you like. And so for that, no extra twisting happens, just the whole diagram rotates by 90 degrees. So if I start with a tangle right here, then the effect of a rotation is just that the whole thing is going to move a quarter turn. And so for that, I'll sort of denote my G is rotated into that configuration over on its side. Okay. So each of these dance steps, I guess, is going to take our old tangle and produce for us a new tangle, right? Because what defines a tangle is the fact that we have these two ropes and that the ends of the two ropes are at the four corners of this square that you're standing in. And the ultimate goal, and this is going to take us, I think, a couple classes to really get to satisfaction, is supposing that we do this dance and we tangle up these two knots in some arbitrary fashion, right? How can we assign an invariant to that tangle that can uniquely describe that tangle and only that tangle, right? If that tangle is actually a numerical invariant, if it's actually good enough, then that number that we assign to it should carry enough information for somebody to figure out how to untangle that tangle. So that's ultimately what we want. Is not only is that number going to be meaningful as a name for the tangle, if you will, but the arithmetic involved in how that number was created is also undoable, right? It will let us do an arithmetic on tangles that can let us untangle a tangle using the same set of steps, right? Just by continuing to twist and rotate in a specific order, can we untangle something that's been tangled? Today's goal is to get us into thinking sort of abstractly about these two operations, the twisting operation, the rotation operation, with a particular eye towards sort of two questions. First being, how do twists and rotations interact one with another? Right? So what are the relationships among T and R that can help us to sort of describe what that structure is? And then the sort of second level question, how do we undo twisting and rotation, right? How do we, if I twist up a rope in a certain way, how do I untwist it using this same set of two operations? These are the only things in our universe for today, are twists and rotations. This particular twist and that particular rotation, the combinations thereof. So we found out that T and R don't commute one with another, right? That in general, if we start with a tangle in its home position and then we do TR, we end up with the tangle rotating 90 degrees, but then we introduce this twist up here on the top. And RT, the tangle, ends up in the same spot, but we end up with a crossing on this side instead of on the top. So TR and RT are not the same operation. Even though if we did them both to an empty tangle, actually we still wouldn't end up with the same thing because, well, RT on an empty tangle is going to give me another empty tangle. Let's return to this question now of what is the inverse of T? How do we untwist a twist? What is the inverse of T? And we want the most general answer to this question because we already convinced ourselves that if we started with empty tangle, we did one twist to it, so that would give us this, right? That one way to untwist this would be to rotate, and that's going to be this, and then do one more twist. And so we know that starting from an empty tangle, RT is the inverse of T. Right? But what if we do it with a generic tangle? So a tangle that is in the middle of being tangled. Let's call it G here again. And let's see if we can work this out using this cardboard diagram. So how do I undo a twist that's just been done to a more complicated tangle? This is where things get kind of even more interesting. All right, so we now have to figure out how to undo this tangle that's at the end of something more complicated. This one's going to take a little while. We just found out by twisting up this cardboard that even though for starting from an empty tangle, it was enough to just do RT once, and then we were done. Starting with the generic tangle, if we introduce a twist that we want to undo, we ended up having to do RT, followed by RT again, and then followed by one more R. So write that in a word. So we have going from this tangle to this tangle at the end is the identity operation. Right? So on the one hand, it's I. On the other hand, what's the word which is equal to I? R, T, R, T, and then another R.
Oh, sorry.
Right? So this T was the original twist that we introduced. We were trying to figure out what the inverse was. And now I think we've shown that the inverse to T is R, T, R, T, R. Right? So when you write out that whole thing, T, R, T, R, T, R is another name for the identity. Right? And so this gives us another clue to how the generators, the twist and the rotation for these tangles interact with one another. This is another way to create the identity out of a combination of twists and rotations. We also convinced ourselves earlier that there was another way to create the identity, and that was just to do two rotations in succession. Right? So now here are two different relations between twists and rotations that can let us simplify words. And if we want to be fancy, and we might as well, we can write this as TR quantity to the power 3. Right? Okay, cool. And the great part about this is we just did this in general, right? We don't have to worry about what tangle we start with. This combination of 3 repetitions of TR is always going to get us back to where we started. So how do we untwist a twist? Just do RT, RTR, and we've untwisted that twist. So kind of what we've convinced ourselves of is that it is enough to just have T's and R's in our system, right? Because we know how to undo an R just with another R, and now we know how to undo a T as well. So if we want to, given this tangle, 4 T's followed by an R, followed by 4 more T's, and if we want to untangle this tangle, then maybe a strategy would be to kind of go one thing at a time. So I should maybe, to untangle this, maybe I'll try to put a T inverse right there so that then the 2 of those could cancel out. And then if I put another T inverse in there, then that one and that one are going to cancel out, right? So if we were to just write down kind of, if we were to write down what inverse that we want here, the inverse for this combination, this composition of 9 maneuvers, we would have to invert 9 steps, but in which order? This would be...
Or wait, would it not matter because there's 4?
Yeah, in this case it doesn't matter. So
Yeah.
it's a little bit of a weird word to use, but you could imagine that what we're really trying to do is we really need to undo the last thing we did first, right? So last twist or last rotation, that'll be the first thing that we try to undo. So we'll invert the T, we'll invert the next T, we'll invert the next T. So we invert 4 T's in a row, then we invert R, and then we'll invert 4 more T's.
So you said we're working backwards?
So I'm working backwards when I build the inverse, right? So this is a specific case of the general principle that anytime we have 2 functions that we're combining together, let's say A composed with B, that the inverse function for the composition, B inverse composed with A inverse, yeah, right. It's like I use the metaphor with my algebra, remedial algebra students all the time, right? It's like wrapping a Christmas box, right? The first layer of wrapping paper that you unwrap is the last one that you wrapped, right? The one on the outside, right? So unwrap the outer box first, then unwrap the inner box, and then keep going. So I usually say that in reference to using the order of operations backwards to solve an equation in algebra, right? Like add and subtract first. Why? Because we're trying to undo what PEMDAS did. Right. Same principle, just generalized right here. Right? So that's what we would do. And then we know now, based on our previous conversation, what each of these inverses actually is. Right? T inverse is RT, RT, R. So what we could then do is just drop in RT, RT, R into each one of those. RT, RT, R. And then 3 more times. RT, RT, R. RT, RT, R. RT, RT, R. And then, yeah, we've got an R inverse here in the middle. That happens to be the same as R, so I'm just going to throw out the R in there. And then I have 4 more of these T inverses. Ugh. Copy, paste. Yeah, no, so you all are going to need some cardiovascular conditioning for this one. Copy this, paste it over here. So here is one way of writing the inverse for this thing. Now, it may not be the simplest way to write it. In particular, I can already see a couple of low-hanging fruit simplifications that we could make.
Double R's.
Got some double R's, right.
A lot
So
of them.
we have a lot of double R's. Actually, here's a pair, here's a pair, here's a pair, here's a pair, here's a pair. I think that's all of them.
So then we're just left with T or
Can we-
T.
can we-
It's only, I think it's only when it's like the
Starting
Yeah, only starting from the empty tangle is TRT the identity. So I'm going to have this, and then I've got another TRT, and then I've got TRT. Oh, it looks like I have another pair of R's that I can cancel. This one and that one. Oh, no, sorry, there's a T in between them.
Right.
No, that's right. So R, so TRT, R, and where am I? TRT, 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 TRT. So I have TRT 3 times. And then I have 1 R at the very end. Whew. Well, okay, that certainly will get the job done. But again, I'm not convinced that this is the simplest way to represent this set of moves. It will certainly work. Let's try it out. But then I'm going to propose a simpler version of this word when we get down to the actual untwisting. So just knowing what inverses are for R and T, let us build a word which will definitely be an inverse. Okay? But what's the simplest version of this word? We actually started with something that had, so there were 8 T's, and so that must have meant there were 40 of these, and then 1 more of those. So there are 41 symbols in this word. And then we used the basic R inverse is the same as R. We reduced that down a little bit, so we're down to what, like 24 word length. But then somehow this, which is an 18-word length, is the same thing, or at least it worked to invert this tangle. So how in the world can we expect to simplify? Or maybe there is another way to think about what's happening here that will give us a different way to approach how this is all working. So again, the plan today is for us to kind of explore the abstract algebra. So that's what we've been doing here, right? Is that we have these two operations that we can do to tangles, T and R, and we've figured out how each of those operations works by itself, and now we also know how each of those operations can be inverted, right? And so we have relationships between T's and R's that we can use to build a group, an algebraic group, which represents the set of all things that we can do to tangles, right? But where we want to go with this is we want to also associate that group with the ways in which it acts upon other mathematical objects that we might know how to study. For example, the first question that I want to ask is, if it's true that this collection of all such operations that we can do to rational tangles forms a group under composition, so to remind you what that means, is that there exists an identity element, which is the operation of doing nothing to a tangle. Right? I'm going to kind of represent this as it just takes my tangle and it does nothing to it. It has the closure property. So any operation that we can do, what should I call it? Let me call it F1, composed with another operation F2, gives another element of my group. In other words, I'm looking at the set of all possible things that I can do to rational tangles, and they're all built out of T's and R's by definition, right? So if I take any combination of T's and R's and I stick it on top of another combination of T's and R's, then I'm going to get another combination of T's and R's, which is still a part of this set, right? Still a part of this group. And what's the last thing that we needed to know to form the definition of a group besides identity and closure? Anyone remember the third? Inverses. Yeah, and
associativity.
Associativity. Yes, thank you. That's. I don't always write it, but it's important. So let me put it up here.
We just had group theory last.
Yeah, exactly. Associativity, and this is true. By the way, associativity is. Let's see. Yeah, I suppose. Well, associativity is true anytime we have function composition, right? And our goal here is we're thinking of these operations as functions on tangles, right? So if I apply the T function to a tangle, then I get a new tangle whose two side strands have been twisted, right? And so because function composition more generally satisfies the associative property, then this will satisfy the associative property too. But yeah, we need this. And remember, associativity means that if I have three operations on tangles composed together, that it doesn't matter whether I do the first two first and then the third, or whether I do the second and third together and the first separately. That as long as the order is preserved, it doesn't matter where I place the parentheses. Right? So that's the associative property. And then the last one, is inverses. That each F has an F inverse such that when I compose the two of them together, what do I get? I. Yep. So that was kind of when we were thinking about how to undo twists and undo rotations. That's really what we were doing, right? If we can figure out how to undo a T and figure out how to undo an R, then we know how to undo anything that's built out of T's and R's, just by taking the inverses and writing them in the opposite order, right? Even if that gives us a hugely long presentation for that word, at least we know that an inverse exists, right? And that's all that we need to satisfy the definition of a group. So somehow we're under the impression that if we can understand this group, we can understand everything that we can do to tangles to create new tangles, that will tell us everything we need to know about tangles. And one of the best ways to do that is to construct what we call a presentation for this group. Did you do group presentations at all in group theory? Yeah, probably not. Probably not. So we don't have to get too far into the weeds of it today. The short story is that when we write down a presentation for a group, what we're really saying are, here are the generators that make up all the elements of this group. In other words, every element of the group can be written in terms of a combination of, in this case, T and R. Right? So we'll write the generators here in the beginning part of the notation. Generators. And if all I do is write down generators, that means that each of these is its own animal, its own object, and we can do each one as many times as we want to, and it never becomes the identity again. So if we just, maybe another way to say that, is if this was all that I wrote, it's just T and R as my group presentation, then that means that T and T squared and T to the third power and T to the fourth power and all those things are all not equal to the identity, not equal to one another. They're all distinct, right? Every time I do a T, I'm going to get something new, something new, something new, something new. And the same would also be true for R squared, R to the third, R to the fourth. So if I just write T and R as my generators and nothing else in my presentation, then T and R are what we call free generators. Like every power of T and every power of R is something different, something new. And also, without any additional information, we also don't have any way of simplifying any combination of T's and R's one with another. And in principle, they would all be different. Right? There would be no way for us to say that TRT is equal to RTR or anything, right? That with just two generators and nothing else, we can't reduce any words in this group down to be any shorter because we don't have any way of moving any R's past T's or vice versa. So without any additional information, we get what's called a free group. So as it's written, generators only create a free group. We'll see other examples of free groups later on in the semester. One way of getting examples of free groups is to think about, even braid groups are not quite free groups, but we might see some more examples of free groups later on. Free groups are enormous. Right? They're definitely not going to be finite because we already have infinitely many powers of T, infinitely many powers of R. They're all different, and there's no way for us to move any T's past any R's. And so any word that we can write down using T's and R's is going to be different from any other word that we can write down using T's and R's. So free groups are enormous. They're massive, infinite in the best sense of the word. But we spent the first part of our class today discovering that there were actually relationships between these generators. The T's and R's had something to do with one another, even if they didn't commute exactly. We knew, for example, that R squared gave us the identity. And so what that does is it cuts down on my powers of R that I can write. I can write R, I can write R squared, but R cubed and any higher power of R we can simplify. Even R squared we can simplify down. So what this means is that now I can write any word in this group using just a single R interleaved with some T's. Because if I have a pair of R's next to each other, I can get rid of them. So now I've introduced what's called, in a group presentation, a relation. And a relation is just a way of specifying what combination of my generators gives me the identity. Or another way to think of it is tell me something about the inverses of my generators, right? If there are inverses. So when we found the inverse for R, we discovered that R squared was the identity. And then the really interesting one for us, for this tangle group, was we also found out that another way to make the identity is to do TR in combination 3 times in a row. So TR, the quantity to the third, was our second relation. So what we would say is that this is a presentation of a group with 2 generators, T and R, and 2 relations. R squared is equal to the identity, and TR quantity to the third is equal to the identity. And so this is still a really big group. You can imagine that there's still infinitely many different tangles that we can make using the tangle game. But it's not quite as large and infinite as if we didn't have those relations. Those relations give us some way of simplifying long words down into smaller words, we hope. Right?